Okay, let's look at the differential equation we get from an LRC circuit. L for inductor, R for resistor, C for capacitor. So here's the circuit. You got some voltage source, a resistor, capacitor, and an inductor, and I suppose there's a switch in here somewhere to turn the thing on and off. Now, from a basic electricity class, you learn Ohm's law, which is the volts across a resistor is equal to the current that goes through the resistor times the resistance. There's this rule, V equals IR. If you ask an electrician, they have three Ohm's laws because they also have I equals V over R and R equals V over I, which are, of course, two separate equations from this one, at least in the eyes of an electrician. So, a little more advanced is how much voltage drop is there across each of these other things. And as it turns out, this is physics that I'm not going to teach you here, but the voltage drop across a capacitor is the charge on the capacitor divided by the capacitance. Capacitance is essentially a measure of how big a capacitor it is. So the bigger the capacitor, the lower the voltage drop. Right? Which makes some sense to me because the bigger the capacitor, the more charge it can take. So the more it looks like there's just going to be an open wire of stuff going right in there. Right, so not much resistance, at least to start with, until the charge gets big, and then we start having a big resistance and a big voltage drop across it. Okay. The inductor, on the other hand, goes the other way, and the inductor's resistance comes from changing the current. When you change the current, either the magnetic field builds if you're increasing the current, or the magnetic field collapses if the current is going down. So the voltage drop across the resistor is actually equal to the inductance, which is a measure of how big an inductor it is, times the change in the current. Notice that could be positive or negative. If it looks like if the current is dropping, then this looks like a negative resistor is actually feeding power back into the system. Now, in a parallel, this is a parallel circuit. This is a series circuit. In a series circuit like this, the voltage drop across each of the components here is equal to the total voltage across the whole thing. So we have this equation that the total voltage is equal to the sum of the voltage drops going across. One thing to keep in mind is that current is actually defined as the rate at which the charge is flowing. The charge, by the way, on this capacitor is essentially counting the number of electrons. It's measuring coulombs, which is a whole bunch of electrons. So when you measure current is you essentially put up a gate on the wire and you say, how many coulombs per second pass through my gate? That's what current is. The more that passes through per second, then the higher the current. So the current is actually the rate of change in the charge, which allows me to substitute that here. And where is it? Where is it? I is the derivative of Q. That gets moved down to here. And so the derivative of I would be the second derivative of Q, and that gets put here. So I write it this way, and I see this now as a second order differential equation in the charge, right? Q prime and Q double prime. So the charge on the capacitor is changing with time. Now, we take the derivative of this to give us actually a third order differential equation. You might wonder why we do that, but it turns out that by taking the derivative, rather than dealing with the charge, I can deal with the current. So I have the derivative of Q is the current, second derivative of the charge is the derivative of the current, and the third derivative of the charge is the second derivative of the current. And anyway, you end up with the derivative of the voltage over here. Now, there's really two situations we have with voltage, and one is that the voltage is DC, so like a battery, in which case the voltage is a constant, and the derivative would be 0, which would make this a homogeneous equation. On the other hand, we might think of it as plugging it into the wall, and our voltage source is an AC voltage source of alternating current, which is actually a sine curve or a cosine curve. And the derivative of a sine curve or a cosine curve would be another sine curve or cosine curve. So the things that we're going to be looking at are either where this equation is equal to 0, homogeneous, because we have a DC voltage source, or you're going to have a sine or a cosine over here because you have an AC voltage source. Okay, so the equation you end up with looks very much like the equation that we had for springs. Remember, with springs, let's see if I can scoop back up here to the spring equation. Yes, the spring equation had the mass times the second derivative position. Gamma was the coefficient of drag, and K was the spring constant. So the drag was times the first derivative, and the spring constant times the function. When I look down here at this equation, I see that the inductance is playing the role of the mass. And when we get to class on Monday, and I bring in my bucket of stuff, you'll see what an inductor looks like. It's one hard and heavy piece of metal. And it just makes sense to me that it plays the role of the mass because it's so dang heavy. On the other hand, the resistance plays the role of the damping. It plays the role of the resistance, of slowing things down. And so it makes sense that that should be there. And then the capacitor, in fact, 1 over the capacitor, plays the role of the spring. The bigger the capacitor, actually, the lighter the spring. The smaller the capacitor, the stiffer the spring. Anyway, there's a bunch of problems in the textbook where they give you values of all, R, L, and C, and ask you some questions. It's just a matter of plugging them in and solving the differential equation. You can do that. Remember, in a DC circuit, this will be 0. And in fact, in this section, that's what we're dealing with, is the DC circuit. And we will do force vibrations when this thing is something other than 0. Well, on Monday. But for over the weekend, this should be a 0 right here. Do a bunch of these. Ask your questions by replying to this this post, or save them for Monday. But you can get them maybe answered a little sooner if you ask them in post here.